Gauge type technology. Bore gauge. A bore gauge is used to measure the inside diameter of a hole. Caliper. Calipers provide precise slide movement for inside or outside depth measurements. Custom or OEM gauge. Examples of a custom or OEM gauge are micrometer heads, air gauge rings, custom rings, and go-no-go gauges. Depth gauge. A depth gauge is used to measure depth. It usually consists of a solid base with a protruding rod or slide. Gauge blocks are dimensional standards used to calibrate, check, or set variable or fixed limit gauges. Go-no-go or functional gauge. This gauge is a precision tool for production comparative gauging based on fixed limits, such as a pin plug, ring, or snap gauge. Height gauge. This gauge is used to measure height. An example of a height gauge is a vernier, micrometer, and surface height gauges. Thickness gauges are used to measure the thickness of metal sheets or strips, plastic webs or films, and other thin materials or sections of components. An example of this is micrometers, calipers, laser micrometers, and indicating thickness gauges. A micrometer is an instrument for precision dimensional gauging. An example of this is a scale, digital, and dial variations micrometers. Thread or serration gauge. This gauge is designed for measuring thread size, pitch, or other parameters such as thread plug, thread ring, measuring wire, thread comparator, thread gauging rolls, thread gauging spring, and STI plug gauges. Measurement and measuring tools. The example here are transfer tools. These are tools that cannot be read directly. These tools are made to contact parts. They're locked into place, and then this is measured with another tool. Calipers are used to transfer a dimension to a line of a graduated instrument such as a steel rule. On the right is a telescoping gauge. It is a gauge that transfers an inside diameter to an outside diameter so it can be measured with a tool like an outside micrometer. Provided here is a list of key points to remember when making measurements. To begin with, there's a difference between a reference surface and a measured surface. A reference surface is a fixed surface. A measured surface is a movable surface. And so the proper measurement requires fixing the reference surface and measuring with the movable surface. Also remember, choose a proper tool for measurement. A rule of thumb is a 10-to-1 rule. Select a measuring tool that is 10 times more accurate than the tolerance to be measured. For example, to measure a tolerance of 0.010, pick a tool accurate to 0.001. Remember, unnecessary accuracy increases time and cost of measurement. Finally, use the tool properly. Pick a proper tool for the job. Then develop a feel for constant and proper pressure, and always remember to store your tools correctly. Accuracy and calibration. To begin with, it's accuracy versus precision. Accuracy is the difference between the average of several measurements made on a part and the true value of that part, whereas precision means getting consistent results repeatedly. The next topic is calibration. Wear and mishandling of calibration standards are a few conditions that will affect the calibration of an instrument. Measuring instruments must be checked periodically for calibration and must be in calibration when in use. Gauges that are found out of calibration must be corrected and assessment made to determine the effect on the products that were inspected with that gauge. Continuing along the line of accuracy and calibration is measurement errors. Some measurement errors are observational, manipulative, and bias. Some examples of observational errors are misreading the gauge and parallax errors. Examples of manipulative errors are holding the gauge incorrectly, not locating datums properly, mounting a part on the wrong datum, and not aligning a gauge properly. The last of measurement errors is bias, which can be rounding off your measurement incorrectly or reading a gauge inaccurately. Continuing with measurement errors are gauge errors and part errors. Examples of gauge errors are precision loss, accuracy loss, and out of calibration errors. An example of precision loss is a sluggish or sticking indicator. An example of an accuracy loss is an incorrect gauge block stack or a bent micrometer frame. And then, of course, there is out of calibration error where the calibration sticker ran out or the part was dropped and needs to be recalibrated. Part error examples are within the piece variation, which is a taper or roundness, dirty parts, poor surface finish, and flaws.